Chapter 14 and 15 we combine into one set of notes since they both focus on probability. Here are a few phrases you'll hear in the next two chapters. The first is random phenomena. When we talk about a random phenomena, we're talking about a situation where we know what outcomes can occur, we just don't know precisely what outcome will occur. Take, for example, rolling a die. We know that we're going to get something between a 1 and a 6, but we don't know exactly what outcome is going to result. There's also something called the law of large numbers. Simplified, this basically just means that more data is better. If we were to flip a coin 10 times, we might get 7 heads, and based on that, we would estimate that 70% of all coin flips are heads. Obviously, we know that's not true. If we were to flip that coin more and more times and collect more data, we would see the percentage of heads come more in line with the actual probability, or empirical probability it's called, of the probability of heads resulting. Some of our more unenlightened friends who are not in AP statistics might believe in something called the law of averages. If we were to flip a coin 10 times and get 10 heads in a row, they might believe that the next flip is more likely to be tails because tails is due to come up since we've had so many instances of heads. That's not true. The law of averages doesn't exist. All those coin flips are now past events, and they don't have any bearing on future coin flips. Here we have a problem about a random sample of 78 AP students. Some are in AP Stats, some are in AP Calc, some are in both. And we are going to use this to answer a few questions on the next slide. So the first rule in any probability problem is to make a display of the data. So we're going to go ahead and make a Venn diagram. So we start off by making our two circles, and the first thing we want to place into our circles is always the overlap. So we have 19 students who took both AP Stats and AP Calc. That's going to go in the middle there. Now from here, we know that a total of 27 took AP Stats, which means this whole circle is going to have 27 students in it. If we put another 8 here, these two numbers together total 27. Same thing with these 41 Calc students. Adding 19 and 22 gives us that 41. Now there's 78 people in our sample altogether, which means our full sample space, which is this rectangle right here, needs to total 78 students. There are a few students in neither of these two classes. Adding up the three numbers in those circles, we have 49, which lets us figure out 29 are in neither class. We can make Venn diagrams with counts like we did on the previous slide, or we can make them using probabilities like I have here. I just switched all of those numbers to the percentage where they're out of 78 total students. All right, so let's answer these questions based on the probability Venn diagram. What's the probability that a student, randomly selected student, is enrolled in either AP Stats or AP Calc? That would be all three of these percentages right here added up. Just to note, anytime it uses the word or, we're adding, and we're always including any overlap unless we're specifically told not to. The way it could be written is with the word or they could use this symbol here. Okay, P means probability, okay, of stats or calc. Add them up and we get 0.629. Number 2, find the complement of the probability that someone is a stats student. When we're talking about complements, we're talking about two events that total 100%. Together they make up the full sample space of every possible outcome. So we want to start off by finding the probability of being a stats student. Okay, we want to add those two together and we get 0.357. The complement of that is everything that's outside of that stats circle. Okay, everything else in the sample space. So 1 minus 0.357 gives us 0.653. Lastly, number 3, find the probability that a student takes AP Stats given that they were also enrolled in AP Calc. This one would be written like this: Stats given that they're a Calc student. So here we know that they're a Calc student. We only care about the people in this pink circle, right? Of that pink circle, if we add those up, there are 52.6% of people enrolled in AP Calc. Okay, that's those two numbers added together. Now, of the 52.6% in AP Calc, this is the section that are also in AP Stats. So we just make a proportion, a fraction, with that overlap section, 0.244, out of the total people in AP Calc, 0.464. The problem that used the word or on the previous page was an example of the addition rule. And here's the actual equation for the addition rule here. So if we have two events, event A and event B, we take the probability of event A, we add event B's probability, and we subtract out the probability of both of them occurring at the same time. Here's an example of why we do it that way. It's the same example we just did. So we have 78 AP students, 27 take AP Stats, 41 take AP Calc. If we just add those together, okay, our probability is too large because there's 19 students in both of these classes. So that 19 is counted here, and then it's counted again in the 41 Calc students. We're double counting that 19. So to find the actual probability, we take the AP Stats students. This is really a probability because it's over 78, just like all these numbers. Add the AP Calc students, and then subtract out the overlap of AP Stats and AP Calc students. That gives us our final fraction and our probability. If we have samples or two events that don't overlap at all, these are called disjoint or mutually exclusive. They can't occur together. In this sample of 78 students, we asked, are you in AP Lit or AP Lang? We had 21 saying they're in AP Lit, 38 saying they're in AP Lang. None of the students said that they were in both. So these two events don't overlap at all. These are disjoint events. Okay, if we randomly select one student, there's no way to get a single student who's in both those classes. We did a conditional probability question on the previous slide when we answered what's the probability that a student is in AP Stats given that they are in AP Calc. Here's our equation for conditional probability. Basically, we just take the overlap of the two events, AP Stats and AP Calc, that was the sliver of the two circles in the Venn diagram, and we divide it by the probability of the given. In our example, that was the probability that a student was in AP Calc. When we talk about two events being independent, they're independent if one event doesn't affect the probability of another. For example, if we're guessing on multiple choice questions on a test, those are independent because if we guess correctly on one question, it doesn't affect the likelihood of guessing correctly or incorrectly on the next question. Drawing cards from a deck, let's say we're trying to draw an ace. If we pick a card and it's not an ace, all right, we're now more likely to pick an ace on the next card because now there's less cards to choose from and there's still 4 aces in the deck. Two events are independent if we look at the conditional probability of B given A and it's equal to the probability of B standalone. And disjoint events are never independent. They cannot be independent. So for the addition rule, you want to associate with the word or, and this next one, the multiplication rule, you want to associate it with the word and. We have two events, event A and B, and we want to find the probability that event A occurs and event B occurs in two successive trials. Okay, to find this, we're just going to take the product of the two events. We multiply them together. If they're independent, we can just go ahead and multiply their individual probabilities. If they're not independent, in other words, if they're affecting the probabilities of each other, when it comes to that second event, we need to adjust it based on what happened in that first event. Okay, it's a conditional probability. We don't want to just assume that events are independent. You have to think about the problem and make that decision because it'll affect how you do the problem. For example, you have a sample of 100 M&Ms, 22 are blue, you choose 2 to eat. What's the probability that they're both blue? When we think about this, we have to decide, are these dependent or independent? Is the probability changing as we move through the problem? And it is. These are dependent events because we can't eat the same M&M twice. So that first M&M, we have a 22 out of 100 chance of being blue. The second M&M, one of the blue M&Ms is gone, so there's 21 left out of 99, 0.046. And the last topic is a tree diagram, which really helps us when we want to map out all the different sequences that are available in a problem. So in this tree diagram here, students at a college were asked, how much did you drink over the last month? Did you binge drink? Did you drink moderately, or did you abstain? And along with that, were you involved in an alcohol-related accident? Okay, it's broken out into trees where off of each branch, these numbers add up to 100%. Okay, if we go down one branch, say just the 44% of students who said I was a binge drinker in the past month, we can see 17% were involved in an accident, 83% were not. Again, these add up to 100%, as do these and these. At the end of our tree, on all the branches, these numbers come from the product of all the branches that it took to arrive at that destination. Okay, so all of these events are disjoint. A student would fall into just one of these categories and not more than one. Having this tree diagram created makes it easy for us to answer some of these probability questions. For example, what's the probability that a student was involved with an accident and is a moderate drinker? Well, we have that calculated already, okay, because it's at the end of our tree here. Moderate drinker and accident, there's a 0.033 chance that a student was involved with both of those. Number two, find the probability that a student was involved with an accident given, that's what that line means, that they were a moderate drinker. Okay, we want to go down the moderate branch, which is this branch right here. And along that branch, we can see that 9% of students were involved with an accident, 91% were not, so our answer is 9%. Number three is where it gets a little more complicated. Find the probability that a student is a moderate drinker given that they were involved in an accident. So the reason that this one is more complicated is because we have students that are involved with accidents up here, right here, and here. So our first step is to add all those probabilities together. Okay, so we add 0.075, 0.033, and 0. We get 10.8%, or 0.108 of all students were involved in an accident. All right, of those 10.8% of students, what's the probability that we select someone who's a moderate drinker? Okay, that's this group right here. Okay, so we're just going to take that percentage and put it on the top of the fraction with that 0.108 on the bottom, and we get 0.306 as our answer. All right, we're going to finish off with two examples, the first being a tree diagram problem. In this problem, we have an airline that offers the option of purchasing tickets in advance and purchasing regular tickets. It says here that 60% of customers choose to purchase their tickets in advance. Okay, from there it goes on to say that of the customers that purchase regular fares, 30% don't show up on the day of the flight. Of the people who purchase in advance, 5% don't show up. Okay, we're going to make a tree diagram with this information. So here I have the important information summarized, and let's start with this bit right here. So it says 60% buy advance purchase fares. Okay, the complement of that would be the 40% who don't, okay, or the regular customers. So we would start off our tree diagram with the 60% as advanced, 40% regular. Okay, next up we have 30% regular customers don't show up. The other 70 do show up. Okay, so we make our branch off regulars, and then we do the same thing with advanced purchase customers. 5% don't show up, the other 95% do show up. Any one of these numbers at the end here are just the product of all the branches it took to get there. So what percent of all ticket holders are no-shows? So we have no-shows here, and we have no-shows here. We can just add those together, and we get 15% of all ticket holders are no-shows. What's the probability that a customer who didn't show had an advanced purchase ticket? Okay, so of the 15% who didn't show, what's the probability that our randomly selected passenger came from that group? Well, 3% out of the total of 15% are from that advanced purchase group, which is a 20% chance. Example 2, we have an opinion polling organization that's contacting households for interviews, and it states that the probability of successful contact is 76%. That being said, 1 minus that is 24%, and that's the probability of unsuccessfully making contact with someone in this household. Part A, what's the probability that the interviewer's first successful contact will be the third household on the list? Now, for this to happen, we had to have called 3 households. The first 2 were both unsuccessful, and the third was successful. So we have 2 houses here, both unsuccessful, and then the third house, we had a successful contact. Multiply them all together, 0.0438. Part B, what's the probability that the interviewer will make at least 1 successful contact among the next 5 households on the list? Anytime we see an at least one problem like this, we want to use a complement. There's a lot of different ways that we can contact 5 households and get successes or unsuccessful contacts. For example, we could get 4 that are successful, 1 that's not, or maybe successful, unsuccessful, successful, unsuccessful. Okay, the only situation where we don't have at least 1 that's successful is when all 5 of our calls are unsuccessful. So we want to find the probability of this event occurring and then just find the complement, 1 minus the probability of getting 5 unsuccessful calls. 0.24 to the 5th power is the probability of getting all 5 being unsuccessful. 1 minus that, 0.999.